Hello and welcome back to PC Retro Programmer. In the previous videos on the Bresenham line drawing algorithm, we implemented all of the cases for drawing lines that move down and to the right. So this included the horizontalish case, which was this algorithm here, and then the verticalish case, which was this algorithm here. And we combined those together, and then we used a trick for dealing with lines that are moving up and to the left. Basically, we just switched the endpoints around and drew the line in the other direction. So obviously, if you have a line that's up and to the left and you just draw it in the other direction, then it becomes a line that's down and to the right, and that we can already deal with. So the only cases remaining, and the ones that we want to deal with in today's video, are the ones where lines are moving down and to the left or up and to the right. And of course, we can use the same trick of switching endpoints to turn one of these cases into the other. So let's say we just need to deal with horizontalish and verticalish lines that are moving down and to the left. And believe it or not, we're actually very, very close to being able to do that already with the code that we already have. So let's just think about the horizontalish case. The only difference between a line moving down and to the right and one moving down and to the left is the direction you're moving in the x direction. And the only place that we need to change anything is just the increment of x. So we start at the same point x0, y0, but instead of incrementing to get to x1, we decrement. And that's really all there is to it. Now, of course, remember, we're not actually using a plot function. We're keeping an offset in memory, in video RAM, and we're keeping a byte for a mask and also a byte for the color information, which is shifted by a certain number of bits and kept up to date every iteration. But basically, it's trivial to change our code to go in the other direction. We'll still keep dx and dy, but we'll make sure that these are non-negative, and then the same algorithm will apply if we just decrement x instead. In the verticalish case, there's not much difference either. Again, the only thing we need to change is the increment of x, and that's just this line here. Now, once again, that involves changing a mask byte and a color byte, but this is trivial to change so that this becomes a decrement instead of an increment. And that's all we have to do to make this algorithm work in the verticalish case for down and to the left. So let's take a look at the code that I've written for this, and I've just called this line 4.asm. And this is basically exactly the same code as line 3.asm, except that I've made the changes I just described. Now, there's actually two ways I could have gone about this. The first is the obvious way of just duplicating the two cases that we already have, and then changing them so that they become left moving instead of right moving. And as I said, those are trivial changes that we'd need to make. The other way of doing things, which is always worth considering, is to use self-modifying code. And what this means is that before the line drawing code actually runs, you have an additional short section of code which modifies the line drawing code in memory, so it actually changes the machine code. Now, this turns out to be relatively easy to do, and it works out fairly efficiently. And of course, it will save half the code because you can use the same code for drawing both cases. You just modify it for whichever one you want before you start. The downside, of course, is the modification itself takes time. It has to run before the actual line drawing code every single time you draw a line. Now, that doesn't work out too badly in practice because it's only run once per line, but it still is an additional cost. So what I'm going to do today is just stick with the fast, easy option, which is to duplicate the code and make the appropriate modifications. So let's take a look at how I did all this. First of all, the conditions on the line are now completely gone. This is totally general line drawing code. It'll go from anywhere on the screen to anywhere else on the screen. Obviously, the prelude is exactly the same as before, and so is this first condition. This is actually the one that checks whether we have a line moving up the screen or down the screen. And if it's moving up the screen, we just switch the endpoints around and draw in the other direction, and that gives us a downward moving line. So This means that from this point on, we only need to deal with downward moving lines. And as I said, we already have the two cases, vertical-ish and horizontal-ish, for moving down and to the right. And so we only need to add the two cases for down and to the left. So the next piece of code is the same again. That's just dealing with the offset of the first point. And then we come to our second condition, and this is where the first real change is. So here we look at the sign of dx, and if this is positive, then we're moving to the right, and if this is negative, we're moving to the left. So we really just want to do a comparison of dx with 0 here, and if it's greater than or equal to 0, then we use the original right moving code that we already had, and if not, we need to jump to our new cases for left moving code. So the obvious way to do that would just be to do a conditional jump. Jump if less than to line left, and that would jump all the way down to our left moving code. But unfortunately, that code is too far away. These conditional jumps can only jump around about 128 bytes in each direction. The assembler will actually tell you if you go over, and it'll complain and say that the jump is too far. So what you can do is an ordinary jump, just an unconditional jump, and that can go any distance within the segment. So that's what we actually have to do to jump down to our line left. We have to use an unconditional jump. And the way it works is that if we are not in that case, we'll jump over the unconditional jump. And so that's what this line does here. Instead of checking if we're less than, it checks if we're greater than or equal to and jumps over the unconditional jump. You can see it just jumps from here down to here. That's all it does. And this is only a short jump. So that's how we deal with that. And then the other thing to note is this is a signed comparison. Obviously, this value dx that we're comparing with 0 implicitly is either positive or negative. So this is a signed comparison, so it's JGE instead of JAE. And then our code is exactly the same as it was before. We have the two cases that we had before. We have the vertical-ish to the right, and then we have the horizontal-ish to the right. So this is the code that we already had in the previous video. So then we come down to the new cases that I've added for left moving code, starting at this line left label here. Now at this point, dx is actually negative, and the algorithm requires us to have a non-negative value, so we just negate it, and that'll deal with that. So the only changes we need to make, as I explained, are to change all our increments of x to decrements. But what does this actually mean in practice? After all, we're dealing with offsets and color and mask bytes. So basically, wherever we had an increment of our offset before, this needs to become a decrement of our offset. And wherever we had a mask byte that was being rotated to the right, we'd have to change that to a rotate to the left, and the same for the color bytes. So they're the only changes we need to make, and this explains this next instruction here. So let me just jump down to the pixel code for a moment so I can explain what this is here for. So the code for drawing the pixel itself are these 4 lines here. Remember, we read from video memory, make our modifications, and write back again with this stosb instruction. But remember that the stosb instruction increments di when it's done. And I just said that one of the changes we need to make is to change all increments of the offset to decrements of the offset. So how do I do that? Well, fortunately, the 8086, 8088 instruction set has us covered, and that's what this std is for. This sets the direction flag, and believe it or not, when the direction flag is set, stosb decrements instead of increments the offset. Isn't that cool? So just with one instruction here, we can deal with that. Now, you've got to be careful with setting the direction flag because programs assume that when they start up, the direction flag is clear. So when you're finished with the direction flag, you need to change it back to a clear state. And so down at the end of this block of code, before we return, we have to clear the direction flag again. So it's back to its original state. So the next piece of code is identical because it's just dealing with the remainder of the offset computation and the color and mask bytes for that very first pixel that we draw. So that's identical to what it was before. No change is required there. Here's where we tell whether we're in the horizontalish case or the verticalish case, and we handle that in exactly the same way as we did for the right moving code. Basically, we just compare dx and dy, and if dx is greater than or equal to dy, we must be in the horizontalish case, and so we'll just jump down to the horizontalish case. Now here we can actually use an unsigned comparison, and moreover just an ordinary conditional jump is fine here. We don't have to jump too far, so it's just a short jump. Now the verticalish code is basically the same as what we had before, except that all of our increments of our x-coordinate have to become decrements. And so you see the first difference here in the rotations. Instead of rotating the mask and color bytes to the right, we rotate them to the left instead every time x changes. And likewise, this code was previously complement carry and then add with carry di0, and so we've changed it to sub with borrow di0 so that it will decrement instead of increment the offset at this point. So that's basically all that we need to do to change the code. And so that's the verticalish left case, and this is the horizontalish left case. And this is likewise exactly the same code as previously, except again we have rotate left, and our sub with borrow di0 becomes an add with carry di0. So this is all we need to do to change the actual line drawing code itself. And so now we come down to the main driver program, which I've also made a couple of little changes to just for fun. So what this is going to do now is it's going to draw a whole bunch of lines to test each of the cases that we have. So first of all, it's going to test verticalish right lines, and so there's a loop, and here's where we actually call our line drawing function. And then it's going to wait for a key to be pressed, and it's going to do our verticalish left lines and make sure that those are all working. Of course, we'll be changing the colors as we go so that we actually see something different on the screen. Then we wait for another key press, and as you might guess, horizontalish right, wait for key press, horizontalish left. So it's just basically the same loop that we had previously. There's just 4 of them now, changing the colors each time, waiting for a key press each time, and then quitting. So let's actually assemble this and see what it looks like when we run it. So as usual, we just assemble line 4, and of course we link it, and then we should be able to run it and see what it does. So that looks like all our verticalish to the right lines, and then verticalish to the left. Now we have horizontalish to the right and horizontalish to the left. So it seems to all be working perfectly, and I guess that there's about a second for each of these blocks. So to finish off the video today, what I thought I would do is have a little bit of fun, and we'll write exactly the same thing in Basic. Of course, Basic has a line drawing function, and it's very, very easy to do this, and just see how it compares, whether it can do it in 1 second. Now, bear in mind that Basic actually has assembly language routines for drawing lines, so it should be relatively comparable. So I'm going to use IBM's Advanced Basic from the IBM Personal Computer DOS version 2.1. Let's take a look at what I came up with, and it basically changed into a CGA mode, a different palette than we use, but that's fine. And then each of the 4 different cases, there's 100 lines of each. So if it's the same as ours, it should take 4 seconds. So let's see how long it takes in Basica. And it seems to be a bit slower than our code. It looks like it's going around about 9 seconds, I'd say. So yeah, that is about double what ours takes. So it looks like we haven't done too badly. So even our quite basic code does quite well, but in later videos what I'm going to do is time it very accurately using Michael Abrich's Zen timer, and then we're going to improve the code to see how much faster we can make it go.